go ahead. This one, if you want to take over here. So Jeshwan, if you want to introduce the speaker, that would be fantastic. Thank you very much.
That would be great. I'll be happy to introduce Susan. So Susan is our today's honored colloquial speaker. So she was formerly the Robert Fashioch Professor of Physics and Billis Research Professor in the Department of Physics at the University of Wisconsin-Madison. And in 2018, she moved to the University of New South Wales. So she's a theoretical condensed matter physics physicist who has worked on a broad range of problems in the area of complex systems and has made substantial contributions to the understanding of subjects, including glasses, granular materials, the nonlinear dynamics of magnetic flux lattices in type 2 superconductors, and also quantum computing. So Dr. Coppersmith has served as a member of the NORDITA Advisory Board, as a member of the Mathematical and Physical Science Advisory Committee of the National Science Foundation, and also as the trustee at the Aspen Center of Physics. So she has served as a chair of the Division of Condensed Matter Physics of the American Physical Society, as chair of the section on physics of the American Association for the Advancement of Science, as chair of the Board of Trustees of the Gordon Research Conferences, and as chair of the External Advisory Board of the Kavli Institute for Theoretical Physics at the University of California, Santa Barbara. So she's also a fellow of the American Physical Society, a fellow of the American Association of Advancement of Science, and also a fellow of American Academy of Arts and Science, and most important, she's also a member of the National Academy of Science. So with that, I would like to welcome Susan to our colloquium today.
Okay, well, thank you. So before I get started, I just want to say that it's fine to interrupt me with questions. I think this is one where you put them in the Q&A, but if someone would just let me know if there's something in the chat, that would be great, because I know holding on to a question is always very distracting. And I'll tell you also, like, the goal, I think, is to sort of give you some sense of the kind of research that's going on in silicon, trying to make silicon quantum computing. But the actual, you'll see the thing of the talk is things don't always go according to plan. And so we're actually pretty excited about understanding why things aren't going according to plan in this particular experiment. And I thought that would be sort of more interesting, just to see that it's not just a march of triumph from one qubit to the next, whatever. So anyway, but that's just an introduction. And so the goal is to give you a sense of like the kind of research and what's going on. So definitely, if you're confused, if it's not clear, you should stop me. Okay. So I'm as you heard, I'm at the University of New South Wales, but I've continued to collaborate with the group in Wisconsin, and so the work I'm going to tell you about is done in collaboration with that group. The experimentalist, the main experimentalist I've been collaborating with is Mark Erickson, who's a professor in the physics department, and then the theory I'm going to tell you about was all done in collaboration with Mark Friesen, who's a research scientist at Wisconsin. And we've had a great group with really excellent students and postdocs. And the stuff I'm going to tell you about today was done mostly by Brander Thorgrimsson and Joel Corrigan. And the theory that I'm going to show you was mostly done by Ekmel Erkin. But there's a few other things that you'll see that people's names are on the slides. Okay, so first I wanted to motivate why people work on silicon quantum computing. And so the first step of that is to motivate why people are working on quantum computing. And this part of my talk used to be much longer because I think there's been enough in the popular press and there's enough awareness of the excitement going on with quantum computing that I could make this shorter. So it's actually sort of silicon based. So you can see it really is selling silicon. And basically the point is that making computers more powerful has revolutionized our world and has proven to be a big technological driver. And the progress in that is sort of amazing. So here is a transistor radio for 1954, which obviously was a radio and had 4 transistors, and it cost $50, which is the equivalent of $427 today. Okay. And it didn't do a whole lot. And then this is an iPhone XR, which actually is the phone I have. And it has, we can do this, 7 billion transistors. And as you know, it's not the latest one, but I was doing a price comparison, and the latest one always has a little price premium. So going back a little bit, this is, I think, just from the, I think it was from the Apple website, but I might have done it on eBay. But new and unlocked, factory unlocked, it's a little more than a transistor radio was in 1954 in constant dollars, but it has, as you can see, billions, billion times more transistors in it. Okay. And for the same price. And so this is here, a picture of Moore's law and the number of transistors as a function of time. And it's an exponential law. And this is, again, the famous Moore's law. And it's been going on for a long time. And up till now, Moore's law has basically been done entirely by making the transistor smaller. Okay. Now this is just in PowerPoint. This is by no means to scale, but it's just you have a transistor, which, and again, this is 1970, but you have they're big, now they're small, and in the latest iPhone, since I wasn't doing price, I used the latest iPhone. The chips are 5 nanometer chips. And so here's this plot of feature size versus year, and we're in 2020, and you can see that it's like we're right on the plot. Okay, and actually, I should say that if you look in detail, Moore's law is has variations in it, and there's a little kink here. So things actually got better, and this is if you look at memory, there's a similar thing. So Moore's law is not a perfect law because it's a statement about progress, which is no longer, is not uniform. But this little kink is due to a thing called chemically enhanced photoresist, which I didn't even know about until recently. But it really, there was this, we're going to run out at a micron. Moore's law's got to run out at a micron, and then there was a technical advance that caused it to continue. But this time, for sure, we're going to run into a problem with Moore's law. And the reason is that we're really getting down to the size of atoms. And so this sort of well-known way of making progress that has led to, a scaling of 9 orders, at least 9 orders of magnitude in consumer electronic devices has, this way of making progress is coming to an end, and we really think this time that something else will have to happen. And it's not a statement that there can't be progress, but it's saying that the way that just making everything smaller is no longer the way to make to get more computing power on a chip. Okay, and again, this is 10 nanometers, and again, the current your phone, if you went out to buy the new iPhone 12, has, the feature size is this big. Okay, and so clearly, you've only got one factor of 5 to go. So, and so people have been able to plot this graph for quite a long time. And again, we're right on the graph. But you can see, like, you hit 20, you hit here, and there descends. Okay, and so, and people have seen this, and so there are like various things that people are thinking about in order to, continue to make progress in making more and powerful computers. And one of the ways that has gotten a lot of attention lately, again, people have been working on it for a while, but now it has sort of hit the popular popular consciousness is quantum computation. Okay, and I'll just sort of point to this, which is the quantum computers are inherently more powerful, have the potential to be more powerful than classical computers. And it's just an engineering problem to make them, okay? And that's what my talk's going to be about. Now I chose the Google computer. It's an amazing technical development to be able to do this. And again, I have a section of my talk that I decided not to give because I'm sure you've probably heard it about, the types of why this is using quantum mechanics to make computers can be more powerful. But building it is a real technical challenge, and that's what my talk's going to be about. And I do want to motivate why silicon, which is that this amazing Google computer, and it really is amazing, has 53 qubits. I heard today that it was a 54 qubit device, but one didn't work. But in the meantime, they've made a bunch that actually have 54 qubits. But if you want to do, there are certain applications, and many applications, let us say, where if you want to make a quantum computer that will solve certain hard problems, you really need a lot of qubits, right? And the thing that got everything rolling was a thing called Shor's factoring algorithm. And people have worked out that if you want to run Shor's algorithm, you really need millions of qubits. And so saying like we want to develop the quantum computer is one thing, but then if you go straight to, and we want to make a big quantum computer with millions of qubits, how are you going to do that, right? And this idea that you're going to need to scale up to, really a lot of qubits is sort of the fundamental motivation behind silicon, looking at silicon. Because the thing I showed you, the whole point of, not the whole point, but one of the points of showing you the incredible progress of classical silicon electronics was to point out that, we just carry around every day, our phones, which have, of order 10 billion transistors that, work, and you can drop it, and, you can put in the rain, and it's all reliable, right? And that did not come cheap, all right? And so the idea of the kind of quantum computing I work on is, to say, we want to leverage all that investment that has gone into classical electronics and ask the question of, can we make a quantum computer that is as similar as, uses technology as similar as possible to what classical electronics uses now? Okay, and that, started out as a totally non-trivial question. And actually in this field, it took quite a long time to be able to make the first qubit. Okay, so you'll see I'm gonna talk mostly about just individual qubits, and the state of the art in silicon quantum computing is really on that sort of, coupling to and getting a really high fidelity gate. I mean, that's not a totally reliable process yet. But the idea is, if you can figure out how to do it with this technology, then you can leverage all of the investment that has gone into classical large scale computation and take advantage of it. And that might help in this quest for getting a really big quantum computer. So, so that's the motivation for what we're doing. And so what I've got here is, again, plausible path to large scale scalability is, I want to be a little honest. I don't want to overdo the honesty, but I want to be a little honest, where this does not address the control problems and the heat problems. This is just a statement about, being able to get a lot of devices in a small area and have them all work. Okay, and that classical silicon electronics has demonstrated is possible. But the second part of, you're using the same technology for the classical electronics and the quantum electronics, and in principle, you can make them on the same chip and things like that. I mean, this one, the integration is like built into the problem that we've posed ourselves of like making a quantum computer that looks as much like a classical computer as possible. Okay, and then just to show you, sort of pictures. This is I got this picture of a classical transistor actually from a in our theory report for 1988, but it's like, it's actually, this is an amazing electron micrograph because it's sort of this tilted view. And if you know about electron micrographs, you should be oohing and awing at this thing, but it's metal gates on top of silicon. And this is, I'm going to show you some data from this device, which was the first qubit we ever made. And it's just metal gates on top of essentially silicon. Okay, and even this is a micron in 1988, and these are 100 nanometers. So see, the length scale is similar, even if it's not, it's smaller, but it's not that much smaller. So you can make a working qubit out of a device like this. Okay, so let me tell you a little bit about the actual experiments that Mark Erickson group does, and hopefully in the course of all this, you'll get a sense of the theoretical, what we bring to the table on the theoretical side in terms of trying to come up with ideas and calculations to make things work better. Okay, so the overall idea I've told you is that basically what happens is that you have silicon, and then you use metal gates and you apply voltages to them, and it does two things. One is that it creates it creates a potential that electrons can sit in. So in this business, if you have an electron in a device like this, it's called a quantum dot. It's like, a voltage, you put on these voltages and you create a favorable energy landscape to put an electron here. And then you design the gates so that, in all the qubits are going to tell you about, there are going to be two quantum dots, and the electron's going to be moving back and forth between the quantum dots, and then you control that, and that's how you make your qubit. And so in these are metal gates, and then this light blue thing is actually a very thin layer of silicon, and that's where the electrons live in the qubit. Okay, and also this is the measuring. QPC is quantum point contact, and that's how you measure the state, is we're going to measure current going through this quantum point contact. But again, everything's living in this layer. And in the particular devices that Mark Erickson works at, this silicon is sandwiched in between two regions of silicon germanium alloy. Okay, and the idea is that this creates a very nice, clean, what's called two-dimensional electron gas, where the electrons live. All right, and there's another way of making quantum dots in silicon, which is that you do what's called silicon MOS, metal oxide semiconductor. And there, what happens is you put the gates on top of an oxide layer, and then the electrons live at the oxide interface. Many things are very similar, but there you have more disorder because of that oxide interface is more disordered. So the idea here is that you're making a cleaner interface, and then there are certain advantages. But then, of course, then when you get into it, there are certain disadvantages also, which the difference in the silicon germanium compared to MOS was what led to the interesting things I'll show you at the end of the talk. Okay, so anyway, again, what you do is you apply these voltages and then you get the electrons in there. And what's really handy is that the same gates that you use to define where the electrons go, you also can use to control the qubit. Okay, so I see some questions. Is the classical data feature size versus year based on ARMs, reduced instructions? So the answer to that is, I don't know. I got the thing from Wikipedia. That graph I showed was from Wikipedia, so you can take a look and see what they tell you there. Everything I know is on the graph. Okay. All right. Oh, Daniel Adams is going to answer this question live.
You just did. I'm just bookkeeping for you.
Oh, okay. All right. And is building the most sustainable, or is it the easiest way? Oh, okay. So is building qubits as similar as classical qubits the most sustainable and effective way of building a qubit? So now I'm going to be slightly philosophical, and I'll say probably not. But one of the things I find super interesting about the field is that there are all these communities of people who work on different systems. So there are cold atom people, there are the superconducting people, there's ion trap people, there's a whole bunch. And what's super interesting to me is that everybody's been able to, not everybody, but there are many, many different ways of making qubits. And I think one of the things that that I see as the future is that probably there will be one technology that takes over the qubit business, but using quantum coherence, I think, is going to be much more general. And looking at all the different architectures, the different platforms in which you can make qubits, I think what's going to happen is that then we'll be able to take advantage of being able to control the quantum coherence and use it for other things. And the thing that is like right now, people have been looking at a lot are sensors and things like that. But I think I think it'll be like the laser. When the laser was developed, there was this, sense of like, well, what's it good for? And then once people had it, there were just all sorts of applications that emerged once it existed. So I think what's happened with the qubits is that that's been a really great, well-defined goal. But what's going to take over the quantum computing world will be one technology, but then there will be all sorts of other applications for these kinds of devices. So, and again, this idea of like, I could have a lot of quantum, I could make a lot of them all in one place, I think is an interesting thing to do, even if in the end, the large scale quantum computers that are used for quantum chemistry or whatnot are made out of some other technology. I still think it's an interesting thing to do. So that's my answer to the, is this the right technology? I'm arguing there's more than one way that we'll figure out things to do, and it's really interesting to see how quantum coherent you can make, how you can engineer systems in different platforms. Okay. Do you have to use time-dependent voltages due to hyperpolarization, like you have to use an ion traps? That one, I'm going to say no, but I think I'm going to answer that question in the sense of I think you'll get a sense of how you manipulate the qubits when I go further. So I say don't say it's answered, and at some point I'll ask whether it's answered, and so now the heat is on. At some point I'll come back and say, did I answer your question? Okay, so I won't do that one right away, but hopefully I'll make clear exactly how you drive it and how you're operating the qubit. So that's coming. Okay, great, and thank you for the questions. Out there. Okay, all right. So okay, so let me get going on that. All right, and so let me just tell you where we sit in this world, because again, whenever you're, I told you about silicon. So in the quantum computing world, there are lots of different ways to make a quantum computer. We said, oh, look, we're looking at silicon. But then even in the silicon world, there are many different ways to make a qubit. And so one of the things that we've done at Wisconsin is that we've looked at qubits that have more than one electron in them, and we've looked at several different qubits, but the one I'm going to tell you about has 3 electrons in it and 2 quantum dots, and I'm going to try to motivate it to sort of say why it's an interesting thing to look at. And again, this is this idea of like broadening the scope of quantum coherence that one could study. But then the other thing I'm going to show you about is so some of this is like sort of what got us going, but now what we found, the actual point is to tell you about like interesting new phenomena that happen. And in particular, what we had is a situation where you could take the same device and tune it up, and it would create like many different states, and you could coherently go between lots of different states. And so it was a big surprise. We weren't expecting it. And so then I'll tell you the theory about what we think is going on, which is that we think what's happening is that the Coulomb interactions are causing spatially broken symmetries to happen. And then you have many more possibilities for different states and with different energies. And then the fact that you can drive coherent, they're called Rabl oscillations between them, is many different pairs, was to us a huge surprise. Anyway, so that's what we're going to tell you about, and we don't really understand everything about the system, but I think the fact that you can tunably get into various regimes in this very straightforward way, I think is actually pretty interesting. Okay, but I'm going to go back to sort of this historical, we were building a quantum computer because that's that sort of motivates a lot of like why people are looking at these things. And so basically just to very quickly summarize what you're trying to do is that what you do is you're just looking at one qubit in this talk. I mean, we've done stuff with more, but I'm going to only focus on one qubit in this talk, again with a double dot and 3 electrons, so it's not trivial, but okay. But I want to make a qubit out of it, which is sort of effectively a 2-state system that I can sort of set going in some sort of quantum oscillation, and I want to get lots and lots of oscillations. So I just keep it going. All right. And if in order to have something that is reasonable to build a quantum computer out of, what you have to do is you have to have it go for a long time before it damps out, before decoherence causes the oscillations to go away. And so there's a figure of merit, which is easy to understand, which is that basically there's the gate time, which is how fast you can cause their rotations in some space, which I will not get into. But you make a gate, and you want the gate time to be much less than the coherence time. So if you want to make a better qubit, you have 2 choices. One is that you can increase the coherence time, and the other one is you can reduce the gate speed. And actually, one way of viewing what we're doing is we're actually like keeping a pretty fixed coherence time, but making the gate speed shorter, okay, compared to other silicon qubits. And so, and that's why we have more electrons, because that helped us get a huge factor of increase in the gate speed. Okay. Okay, but you still need a pretty long coherence time because you need a really high figure of merit, and you need at least 100 of these oscillations to get anywhere. And the path is basically you try to design a qubit with really fast gates, and then you see what the decoherence is, and then you try to figure out what's causing it and make it go away. Okay, and then once you've made one source of decoherence go away, then you find out there's something else limiting it, and then you just keep this going. So you basically can do this forever. Okay. So, so everything I'm going to show you in terms of like the qubit that we have and the quality, and to give you some sense of like why this kind of approach actually can get you somewhere, I'm going to show you graphs that look like this. Okay. And so basically, again, what you do is you prepare a qubit in some state or another, and then you set it going where it's going to, it's a qubit has 2 states, and we call one of them 1 and one of them 0. And then you start it off in 1, and then you sort of set a gate going where it goes from 1 to 0 to 1 to 0 to 1 to 0. And you want to, and then you do that many, many times. And if the whole thing is coherent, then what happens? Then each time you do it, you get exactly the same result when you measure as a function of time. Okay, but if things are not perfect, then what happens is that the oscillations decay away. Right, and that decay time is due to decoherence. So what you do is you sort of set it going, and thing decays, and typically what happens, there's some other control parameter, which in my talk is always going to be some voltage that this is time, this is the voltage, and you just basically count these white strips, and the number of white strips is basically your figure of merit. Okay, and you need like 100 white strips to get starting to be able to get a scalable qubit. Okay, so okay, and so now I'm going to tell you about the qubit. And so this is true in general for a qubit, where it's a 2-state system, and so the Hamiltonian is a 2x2 matrix, and it has to be permission. And for many, many qubits, including the one that I'm going to do, basically it's a real Hamiltonian. So there are only 2 numbers that describe it. There's the off diagonal term, and there's a diagonal term. All right, and there's a constant. So the trace is 1 because sorry, the traces of the Hamiltonian is 0 because you could always add a constant to it. It just changes the 0 of energy. Okay, so it's a 2x2 matrix, and then there's a way to think about the qubit, and for what I'm going to do, I'm going to think about it being an electron that can go from one side to the other, and there's this this double quantum well, and I have voltages, and I can move them relative to each other, and that's the asymmetry epsilon, which in this business is called the detuning. And then there's a matrix element, which is, tunnel. The electron can tunnel from one side to the other, okay? And everything can be controlled by voltages, but in these experiments, typically the tunnel coupling is fixed and the thing that you vary is the detuning. Okay, so everything is done just by moving the, tilting the well back and forth like that, okay? And so then what you want to do is you want to, again, in principle, you can control delta, but in practice, you tune it up to a value you like, and then you let it stay fixed. And then just by controlling this asymmetry, then you can do all the gates you need to do. And again, the trick is that you want to do that and still have it be coherent and not lose, and have it stay, keep your quantum coherence. Okay. Okay, and so, so then the only thing happened here is I calculated the eigenstates of this 2x2 matrix. Okay, so this is energy versus detuning, and again, here it's linear, and then there's the minimum is set by the tunnel coupling delta. And hopefully this looks really familiar because you've done the two-state system. Okay, and so again, and so now the idea is you just want to vary delta in some way that causes you to be able to get from one state to any other state. Okay, all right. And actually, let me, for what I'm going to do in this talk, what we're going to do for almost everything in the talk, we're actually going to make delta go back and forth like this and resonantly, okay, so that you excite it across this gap, okay, and that's all you need to be able to do to make a qubit. All right, so but now again, the issue is decoherence. All right, that in these systems, in semiconducting qubits, the dominant source of decoherence is charge noise, which is just charges moving around far away, or some sort of electrical noise, which is some sort of electric field acting on your device. And what that does is it basically changes the detuning, because remember, the detuning was the difference in the energies of these two states. And if you have an electric field, right, that is going to change, there's E times the separation, and if E is changing, then this detuning fluctuates back and forth. So when I look at this energy, I think I know the detuning, but I have on top of the voltage that I've applied, I have the noise in the device. And so then what happens is that these sort of parabolas with the square root on them, they're moving this way, okay? And so if I, so this is the detuning I think I'm at, and the qubit frequency is going up and down. Okay, and again, I'm trying to, I'm driving it with this AC at the frequency I think it wants to be, but the frequency at which it is fluctuating in time, and that's the main source of decoherence. Okay, and I will say that it wasn't known until people looked experimentally that this was the dominant source of decoherence, but it's, it just is, okay, because people have measured it and we know that it is. And that is the dominant source of decay of these oscillations. And so the first thing that people tried was they said, well, okay, but the thing is, if you're going to do that, the best place to sit is a minimum, because the delta qubit energy, delta detuning is 0 at the minimum, right? And that actually was, again, way back in the day. For superconducting qubits, I had the same problem. And quantronium is just you operate at that point, okay? And this is the oscillations that you get from a superconducting qubit, again, back in the day. What was called a Cooper pair box, and you can see, it oscillates, and it's certainly much better than not operating there. But you can see also that you have nowhere near 100 oscillations. Okay, and surprisingly, one might say that people had not actually done this experiment for a charge qubit in silicon or in any semiconductor until this was like 5 years ago. We did it. Mark Erickson did it in his group, and again, this is just a charge qubit. You can just sort of park yourself at the sweet spot, and you can drive it AC, and you get quantum oscillations. But you can see nowhere near 100 quantum oscillations. So you got to do something if you want to make a qubit that you're trying to get this coherence up. Okay, so I'm going to tell you about the qubit we developed with again with multiple electrons in it that really was a big improvement. Okay. And and I did want to say that the strategy was inspired by the transbond, which is a superconducting qubit with much better coherence. It's the technology that is used in all of the superconducting quantum computers that that you hear about. And the idea of a transbond is again, what you had before was a sweet spot, but what they did is that, like, we want to make that thing so that it's not just the lowest order, that the two qubit states have the same energy, but you want to make it like a much more extensive thing so that you're much more insensitive to the charge noise. So so that's one way of thinking about it. Okay, the other way of thinking about it is that we can say, well, look, if you want to make a good qubit in silicon, you want it to be insensitive to charge noise, and the way to do that is to use the spins. Okay, and so you can make singlet states and triplet states, and if they have the same charge distribution, they'll be affected the same way by the charge noise, and that would be good. Okay, but the problem is you have to come up with some way of making a fast gate. And by making more electrons, you can sort of make spin transitions by moving charges around. Okay, and that was this idea of the hybrid qubit. So one way of thinking about it was thinking about how to make charge states that weren't sensitive to electric fields. And the other way of thinking about it is that you have a spin qubit that you can gate by moving charges around. Okay, so it's a hybrid between spin and charge. Okay, and so this one's done in the second way. Okay, and the idea is that you have a singlet state here and a triplet state there. It's a slight bastardization because the actual singlet state is up, down, minus, down, up, and here's a triplet state. It's a particular triplet with all the same spin quantum numbers. And I want to get from one to the other. And again, I don't want to do it by flipping spins because flipping spins is slow, but I can do that by moving charges. And here's how you do it. And there you go. Okay. And now that this is obviously done in PowerPoint, but okay. So now we're going to do it. The original experiment that we published, we did this way. We actually did it this way. We moved one electron over and the other electron back, and there you go. Okay. And again, I could turn that into equations, but this is legitimate, even though it looks like it's only a PowerPoint animation. It is actually what you do. Okay, and so the point is that by moving charges, which you can do quickly with these, you apply voltages and you move electrons around, you actually can change the spin state in one side. Okay, and the thing is, the total spin state of all three electrons is conserved. Otherwise, you couldn't do it with just voltages, but you think of this as your qubit, and you're good to go. Okay, so I give you just a couple of slides on how the qubit works. Okay, and so the idea is that you start with you have three electrons, and what's going to happen is that one of these electrons can be either on the left or on the right. Okay. And now what this is what's called a detuning diagram, is that this is the energy and this is the detuning, which again is, you're moving the two wells from side to side. And so here's the state, you have the singlet state here where you have two electrons on the left. Okay, and then when you increase the detuning, you move the right guy down, and so then the energy of the left guy goes up. And then this is the state with two electrons on the right, and its energy comes down. And then you have an anti-crossing here because you have the tunnel coupling. And so then you get the avoided crossing that I showed you before. Okay, so but now we've added more electrons, and so you have a singlet state here, but there's also a triplet state. Okay, and so here's a triplet state, and there's an avoided crossing. And that's on the left side, and you can do the same thing on the right side, right? Here's the triplet state, and then you have avoided crossings there. And now I've drawn it in this sort of funny asymmetric way where the tunnel couplings are not the same and the singlet triplet splittings are not the same. And the reason I did that is that these are actually obtained by measurements from this device. Okay, so what we did is we figured out all of these energies. And what I'm going to show you is on this side. Okay, and again, this was after we worked on it for a while. We realized that we would be happier working on the side where the singlet triplet splitting was less. And this singlet triplet splitting is essentially the qubit frequency. And again, the way you actually drive it is you apply AC. You park yourself somewhere, and then you have some qubit energy, and then you just apply AC at this frequency. And then from that, you can make all your gates. Okay. And again, what happens here is that, again, this is detuning. And so if you move to the right, the singlet and the triplet, essentially, the other electron and the other dot, just decouples, like you just don't see it anymore. And then the singlet and triplet are, they're just independent, essentially. And so to do the gating, you want this thing to be not too far from this anti-crossing. Okay. All right. But this also gives a certain tunability to the qubit. Okay, and so basically that's the qubit. And what happened was that, so first of all, this was the first experiment that we did, and it was, as you can see, better than that charge qubit was, but not a lot better than charge qubit was. But now we had more things to work with, and so then we were able to really work at improving the qubit. And so now I want to tell you how we did that, because that's what led to the sort of the interesting physics that I wanted to get to in the talk. Okay, so how do you get from here to there? All right, and it turned out the idea was really very simple, and that is that, okay, these were the things I showed you before. Okay, so I didn't worry about the top state. So basically, this is the singlet from the, with 2 in the left and 1 in the right, with the singlet in the left and 1 electron on the right. And then here are the singlet and triplet states with 2 electrons on the right. And this is the tuning that I showed you. And now what this is the qubit frequency as a function of detuning. And you can see that it's flat out here, but where you actually operate it, it's not this dispersion, it's called the qubit frequency versus detuning, varies. So again, the whole thing is the detuning is fluctuating a little bit. And then the qubit frequency is fluctuating. But if you just futz with your tunnel couplings, if you tune them up, you can actually cause this thing to be quite flat. Okay, and that was how we, got from here to there. We just eliminated the source of dephasing by working on this, by tuning the tunnel couplings to make the dispersion as flat as possible. Okay, but then we realized that, and we have theory on this, and then we said, oh, and then it turned out the second leading source of decoherence came in, and we figured out how to get rid of it. And we said, okay, great, we're going to do a new device, and we're going to get to really, really high fidelity. Okay, so here's the new device. And again, the plan was that we were going to take this device and tune it up. Again, what I mean by tune it up is you're adjusting the voltages on all these gates. Again, so this is the double dot. Okay, there's a left and a right. And then this is the charge sensor, CS is charge sensor. And so you're applying, you apply voltage across the charge sensor. And basically, I forgot to tell you, but I will, just so you know, what you're doing is that, you have this electron. And if you think of it as a charge qubit, since it's hybrid, it has a charge character. If you move an electron closer to the charge sensor, it makes the channel that the electron's going through a little narrower, and the resistance goes up. So you're just measuring the resistance of this channel using this charge sensor. And because there's this charge character, you can directly figure out which side, which quantum dot your electron is in. Okay, so that's how the measurements are done. Okay, so we had the same plan. We were going to do this. And basically, again, when the thing which I didn't have a thing handy, so sorry, but if you run this qubit not trying to make this, adjust the tunnel couplings to get this flat dispersion, it looks totally normal. Okay, but then we were like, okay, let's tune it up. you know, but not with a really long coherence time, but we're like, oh, let's tune up, get a long coherence time. And then when you do that, it turns out that you get all sorts of extra resonances. Okay. And I'm going to walk you through this. I'm going to show this later, but basically there are 7 different resonances that you can drive coherently. Okay, which is not what we were expecting. I mean, what I showed you before was a qubit with 2 states, right? And so we started with something with 2 states in the energy window, and then all of a sudden there are all these states in the energy window. Okay, so so I want to tell you why that is, okay, or why we think that is. All right, so first of all was the finding 2 was already a problem, okay, because we thought there'd be 1. But then, so Joel did these experiments, and so basically this is, you set the thing up, you fix the tunnel couplings, you go to some detuning, and then you apply that AC. So this is what the picture is you apply this AC. And what these plots are is that on the one hand, there's the duration of the AC, which is called T-Rabi, okay? And then the other one is a voltage, which essentially is, you know, is just the detuning for purposes of this. Okay, all right, and so you see these characteristic oscillations, and you know, and more or less what's happening is this is not exactly what I want to be doing, but you know, what's happening is that, you know, this is time, so this is the minimum frequency, so it's sort of here, and then the frequency goes up as you go off the minimum, and so you get this characteristic shape. But this one, she's driving the AC at 8 gigahertz, 8.3 gigahertz, and then she goes and everything else is exactly the same. She sees Rabi oscillations at 7 gigahertz. Okay, so there's another minimum at 7 gigahertz. So the only way to do that is to have additional levels. Okay, that, you know, that you're able to you know, that you can drive different energy separations. You know, you're driving at different frequencies because they correspond to separations between energy levels. And so the question is, well, where did that come from? Okay. Oh, and not only that, there's more of it, right? So here's another one. Here's 6.15, and so obviously, you know, something else is going on. And so this is the experiment, okay? And so then what we did, I mean, the first thing you do as a theorist, now I'm telling you about me, of course, but still as a theorist, I mean, you look at this, and again, everything I showed you up until like this slide looked, you know, pretty normal, and the whole thing was designed to have like 2 states in it, and then you get this. And again, you can operate this in some other tunnel couplings, and nothing like this happens. So it was a huge surprise for us. But anyway, so what we did is we just said, well, let's just make a phenomenological model and just put in a bunch of resonances and see what happens. And so that's what this is, where basically this theory is just phenomenological. Let's just put in energy levels and put in some matrix element between them and see if you can get something that looks like the data. And the answer is, yeah. So you see like this thing like this, and you can see that, you know, it's these things where basically these are slightly different experiments. What happens here is that you I should tell you what the experiment is. Oh no, this is okay. These are Rabi experiments where basically, again, you just put the thing on, you're driving Rabi oscillations, and then you see evidence of more than one. Okay. Okay, but not only that, but, you know, 1, 2, 3, 4, 5. Okay, I showed you 5 right there. Okay, and so now there's another experiment you can do, which are called Ramsey experiments. And so what happens in Ramsey experiments is that you start in the 0 state, then you apply a pulse that turns you into a equal superposition of 0 and 1. And then you just go somewhere and let it evolve. And so you have 2 states, and then you accumulate a phase, and the relative phase between the upper state and lower state is just a measure of the qubit frequency at that detuning where you're hanging out, just letting the phase evolve. Okay, that's what's called a Ramsey experiment. Then you go, and then the rest of it you think of as you go back and you measure. Okay, that's what the second half of the pulse does. Okay, and so again, Ramsey does usually quite simple things, but here you can see that, you know, again, you do the Ramsey experiment at all the, and you get, you know, all sorts of complicated patterns. Okay, but first of all, the patterns, but then second of all, you can do the Ramsey at all the places you drove the Rabi, and so you can get, you can really map out the dispersion over a very broad range of detunings. So that's the point of the Ramsey experiment, that everything works, right? You can do Rabi, you can do Ramsey. It all works. And when you do all of that, you find, again, many, many different resonances. Okay, so these points are from Ramsey. It turns out, like, from Ramsey, you just get more data from one scan. And because again, you're measuring as a function of detuning when you do this. Okay, so again, everything is the same. The tuning is the same, but you drive it to, again, two different Rabi frequencies, and what you can do Ramsey here and Ramsey there. And you can see what a beautiful job that Joel did in making a really flat dispersion. So like before we actually tried to run the qubit, we were like all excited. We're like, oh yeah, this is gonna be like a super coherent qubit. It's gonna be gorgeous. But then all of this happened. Okay. So what happened? Okay. So so now here's where, you know, our theory came in, to try to just figure out what could have been going on. And what we think, I should tell you what the theory was. Okay, and so what we did in this theory was, and again, since it hadn't been seen before, we decided to do something, you know, fairly substantial in terms of modeling these devices. Okay, and so it turns out in silicon, particularly in silicon germanium, one of the things that does affect the physics quite a lot is what's called the valley splitting. Okay, so I'll tell you what a valley is. It's a conduction band valley. You probably know that or maybe you don't, but silicon is what's called an indirect band gap semiconductor, and what that says is that the minimum of the conduction band is not at k equals 0. It's out pretty close to the Brillouin zone boundary. Okay, and if you have bulk silicon, there are 6 degenerate valleys. Okay, in these heterostructures, what happens is that, you know, it's a sheet, and it's under a lot of tension because germanium is bigger than silicon, and so that breaks the valley degeneracy. And so in these heterostructures, you have basically 2 valleys that enter, and the finite size of the vertical direction of the well breaks that further. Okay, so there, you know, there's no real valley degeneracy, but the amount by which the sort of what are called the Z valleys is broken depends a lot on the quality, on the properties of the interface. Okay, and it turns out that no one had really put that in the valley physics, which depends on the interface on the atomic level, together with strong interactions, the Coulomb interactions of the electrons. And we realized that if we ever wanted to do anything really quantitative, we had to really understand that physics. And so Ekmel Erkan had, he put together a full configuration interaction calculation of being able to calculate the properties of the electrons in these wells for silicon germanium, where there's valley degree of freedom, you know, really matters, and where the interface properties are crucial. Okay, so that's what this is. Okay, and again, no one had done that before. People have done full configuration interaction calculations for quantum dots, but not with valleys. And again, valleys really add to the complexity. Okay, and it happened that Ekmel was working on this and was just getting this program working, and then this happened. Joel's experiments happened, and so he said, "Well, let's see if we can really model what's going on in Joel's dots." And what happened was that Ekmel was able to show that, for dots of the size that she was measuring, you actually get these broken symmetry states. So these are called Wigner molecules, and they are known, okay, but no one has done, coherent quantum transitions between all these states. And so we're sort of arguing not just that they occur, but that they can be, driven in a quantum coherent manner. But what happened, so what you're supposed to look at here is that, if the blue is if you have no electron-electron interactions, and I think you noticed that I didn't really talk about electron-electron interactions when I was moving my electrons around. I had two states, right? I said, here I have two resonances that I could have. Okay, but now I turn on the interactions, and in this frequency window that Joelle was measuring, all of a sudden you see like many, many more frequencies that are available. And in particular, there's like some really small ones. And so that, I don't know if you remember, but that's what led to the complication in the diagrams, is that you have one frequency that's really low. And so that means that you have closely spaced frequencies. And that you can think of as, I think one way of saying it is that, that you have these states where, because you broke the symmetry, like this and this are a little different. Okay, and so we're still working on, actually, this is why this is in preparation, is that we're still working on having like a simple picture of how to think about what frequencies you get and what makes them close or far. This was obtained by, the full calculational scheme that I told you about, and just putting in a fairly, a symmetric dot. But the point is, you get all these different frequencies from a system that only had, that was behaving basically in this sort of single electron picture before, where the only thing you had to worry about was Pauli principle. Okay, so we think this is what's going on, and we're actually pretty excited because, again, it's complete. You can make this come and you can make it go away in this totally deterministic way by just adjusting gate voltages. And that to me is exciting because that leads to a bunch of interesting questions of, like, suppose you have a system like this where, there's state one, there's configuration one, which is one way, and configuration two, which is another way. And then you're driving these transitions. And what if you then go between them on the same time scale? What's going to happen? So we're thinking of going in that direction. And again, now we've gotten off the qubit. We've gotten off the qubit track, but on the other hand, I think there might be some really interesting physics there. The other thing that's useful, though, is that because we have Ekmel's calculations, then we know what to do to make this not happen. Okay, and it turns out that if you make the dots yet smaller, then that suppresses this transition. And so for the next device, we know what to do so this doesn't happen. So we have the let's explore it more on the one hand, and the let's not worry about that and make it go away on the other hand. And in both cases, the theory is very helpful in terms of figuring out what you want to be doing. So that's basically what I wanted to tell you about. And I think all I had here is just a summary. Again, the first part was to sort of give you like the story of like how we got into this, why we started thinking about these qubits with multiple electrons in them. And then the second part is that once you have multiple electrons, then there is this possibility of an interesting interplay between, making quantum coherent systems, making qubits, and also the effects of strong interactions that lead, to, sort of broken symmetries and new phases. And I think that is all I want to say. Here are some references. And again, the experimental paper has been posted, and the theory paper we're hoping to post really soon. Thank you.
Awesome. Thank you. That was really awesome. So we do have maybe time for one question. Are you up for one question too?
Oh yeah, no, I'm here. You guys are busy. I'm here. Yeah, but I'm available for however long you need. Okay.
So the students that have to leave at 5, of course, they can.
Yes.
But Nicholas Batteries says, what type of sources of charge noise are present in silicon germanium based qubits? Are these point defects, interface states, surface states? What are we talking about?
Well, that's a great question. I think, what do I say? I mean, the short answer is I don't know, but this is something that people are studying in a lot. I mean, it's a matter of great import, obviously. And there's definitely, in the early days, I think the oxide the oxide interface was, there was evidence that that was a serious source of noise. But then what happens is that processing improves. Okay, and so now there's a group at Rochester. The PI is John Nickel, and he's been studying. And so, again, studying silicon germanium noise specifically. And I would say that based on his experiments and the gestalt of talking to people, people think that probably it's some sort of charge trap near the gates, and that it's more or less arising from, from e-beam damage near, because you're doing electron beam lithography. And it's, and what happened is that what Nickel showed is that the picture we had was that we had charge traps all over, okay, and that it was essentially, the field was pretty uniform because the charge traps are uniformly distributed. But what Nickel showed was that if you look at the charge noise at one dot and compare it to the charge noise at another dot, like temporally at the same time, there, you'd say, oh, if everything was far away, the noise would be sort of the same, and it's not. Okay, and so, but it's not opposite either. But but the picture is, he says that there's sort of tends to be fluctuators right on the dots and charges going in and out. And again, so people think it's from the lithography because the noise at different dots does not seem to be correlated hardly at all. Okay.
From lithography, like residue, or you mean like actual damage, like these defects that he's talking about? So point defects that are induced from the beam itself.
Yeah. And again, nobody really knows. There's just this thing of like, that e-beam damage is an issue. And so the biggest problem in this field at the moment is actually yield, because what happens is that the devices have a situation where you have to put one layer of gates, and then you oxidize, and then you put another layer of gates. And so the yield of not getting leakage between the gates is not as high as it should be. Okay. And again, it's this thing of like, once things start getting complicated, you need really high yield in order to get useful devices. And so it was fine for a while, but as people try to scale up, it turns out that's an issue. And people think it's because like everything is fine, because if you do one layer, you get great yield. But when you put the second layer on, the yield goes down, and people think it's because of e-beam damage to the oxide. You see what I mean? Between the first layer and the second layer. So that's a speculation though. Okay. But people, I mean, if we could eliminate those problems, then the experimental progress would be a lot faster. Okay. Because that's their big problem, is device yield. Okay. So, oh, I forgot to ask about the time-dependent voltages. Did I explain it? We'll say yes. Okay. Okay. Do Wigner molecules behave like cat states in cavities? Okay. There's different ways of saying this. So I will say that there is work on generating cat states using just sort of qubits, done Andrea Morello at UNSW using MOS qubits generated cat states. And his thing was that they weren't quantum dot qubits. They were made with like, dopants. Okay, so there was a phosphorus dopant, and there's an electron on it, and then there was a nuclear spin on the phosphorus, and you could make cat states out of those. And then he was able to do, really, really beautiful, cat state type measurements, because he had that if you just have an electron and a nuclear spin, then you can do that with extremely high fidelity in silicon. I actually got the best violation of Bell's inequality that's been achieved, except that it wasn't really a violation of Bell's inequality because the electron and the nucleus were like, they were right next to each other, right? But if they had been, far away, then that would have been a violation of Bell's inequality. So so you can definitely make cat states, okay? And the molecules, again, if you could make them coherent enough, then you could do that, right? Because it is just, they're like qubits, and you can take qubits and you can make cat states out of qubits. But we're not anywhere near. You saw, I mean, they were all coherent, but that was not super coherent. Okay.
Yeah, the reason
again,
I asked,
sorry,
the reason that I asked is that they have these spatial distributions that look a lot like Wigner functions or like Bach states. That's what kind of made me think about it.
Yeah, if you can do this and this and this, I mean, that would be the thing is, again, these things, as you try to make things more complicated and keep them quantum coherent, I think that's a really interesting thing to try to do. So the real answer to your question is, I don't know. Okay. All right. How much?
Thank you.
Okay. Yeah. So sorry about that. But I hear what you're saying. And, but on the other hand, you could say, well, as long as you have two states, then we just call one of them 0 and one of them 1, and there you are. But I think there's just a lot to explore, because there are all these different states, which you can make go and come, go away and come back, which is I think a new thing to think about. How much harder is this setup compared to other setups? Well, I would say that, so the thing is that, okay, there are a couple of things to say. In the silicon world, there were the people who were doing, there are, many groups who are doing like spin qubits. Okay. And spin qubits are definitely much more resistant to the external world than the ones I was telling you about. Okay. But the problem is that if you want to couple qubits together, you have to do something that enables them to talk to each other. And each one thinks the other one is in the external world. So what happens is that you have to have some way of, so then what happens is, like, the coupling qubits together is actually where the sensitivity to the external world comes in. And in the silicon world, it turns out that, like, once you're coupling qubits together, it's all the same. Everyone has a charge noise problem. Okay. Now there are other architectures. So for instance, the superconducting qubits, I think, again, they have their single qubit, coherence is much higher than what I've been able to show you. But again, if you look at the 2 qubit gates that are in silicon, they're actually sort of comparable. They're pretty comparable to the superconducting qubit fidelities. So I would say basically what happens is that if it's not comparable to what other technologies can do on a time scale, on the funding time scale, then people stop looking at it. Okay. So silicon is definitely behind, okay, because the first qubit the first decent qubit was not really there until about 2014. I mean, our qubit was not the first one that was decent, but it was very soon after the first one that was decent. Okay, so now the 2 qubit gates are going up the learning curve. Okay, and so in terms of the first really good qubit, it's like 10 years behind superconducting qubits. And so what we're hoping is to take that separation of time and make it smaller. And if we can't, then that's it. So, okay, the global supply chain, germanium and silicon. Oh, I mean, the real problem with silicon is what, the fifth most common element? I forget. There's plenty of silicon in the world. I don't know about germanium, but no one seems to be worried about running out of germanium either. But silicon's super abundant. The big problem is not so much for our qubits, but in general, our qubits at some point will be helped by isotopically enriched silicon. And so that adds to the expense. But again, all of these things work at pretty low temperatures. And so the cooling expense is actually a big expense. So I think everything's going to be limited by cooling. And that's something where very little work is done on really making that scaling. And that's going to be actually the same for silicon and for superconducting qubits. Okay, so, you know, but again, there is this thing of the superconducting qubits are, I don't know, I forget, like 1,000 times bigger on a side. So, you know, if you get to the point where you solve the, you know, can you pack them in problem, then silicon will have, the semiconducting qubits will have advantages. Order of magnitude price difference. So that is an interesting question. Now, it turns out that I believe this is true, that there are commercial semiconductors made with these kinds of heterostructures, but they are a specialty item. But basically, what happens is that you can get like super high mobilities, much, much higher in silicon germanium than in silicon. And so for really high speed applications, it turns out that they're used. So let's put it this way, between the other problems, the price of the substrate is negligible. Okay, but it's the same now, right? You know, where it's however many $1 billion to make the fab. Okay, but if you make enough of them, then it's amortized over, you know, however many billion people in the world who buy an iPhone. So the cost of this of the devices, I think, is sort of, nobody worries about it. People think hard about the cooling though. The cooling and the crosstalk are the two things that are absolutely the same for us and for superconducting qubits. And so we follow their work on that really, really closely, because we're sort of banking on the fact that, you know, we'll be able to take advantage of all the progress that they make by the time we get to the point where we have as many qubits as they do.
Awesome. Any other questions? So I think we are going to have potentially some faculty stick around if they want to just kind of chat, but it looks like we're kind of out of questions for right now, but might as well leave it open.
I have a question. If you could split the remaining valley degeneracy yourself, could you then test some of the theoretical work that you're doing on the reason for these?
Oh, I see. Yeah. I mean, so what should I say about it? So, I mean, that last degeneracy is split. I mean, that actually turns out to be, you know, determining the qubit
right,
frequency.
but I'm wondering if you could split it far enough that that one of the two states was out of energetic range. Would you then?
Oh, well, that'll be interesting, because the thing that we can do is and again, no one's really looked at this in the silicon MOS, but silicon MOS, because I mean, you know, so just the energetics of it are, you know, all the electrons are like, you know, bang up by the surface, right? And there's a huge, you know, and they're in a very narrow, very narrow potential compared to silicon germanium. And what happens is that the energetics of the valley splitting are different in silicon MOS, and they are out of the window. Okay. And so that's like one of the things that's quite different. And so the thing which we can do theoretically is you just take, you know, you take step one of the valleys out, and then you could look at it in MOS. Okay. Now the thing is that MOS devices, have tended to be much smaller, and it turns out that that's how you make all these effects go away, is you make the dots as small as possible. But it's always easy to make bigger dots. The thing which I don't know is, again, the disorder effects in the MOS devices are bigger, right? Because it's near this oxide interface. And so I don't know whether you can get into the same regime without being like totally dominated by disorder. But we could look into that. That's a great question.
I guess what I'm thinking about is, what I'm going to describe is really kind of tedious and nasty, but if you could thin your existing devices, which is lots of times done through polishing and etching, you could bow them. And if you bowed them, you'd put strain in that other direction. And then you could study the properties as a function of bowing.
So I'm a little confused. I mean, the thing is, I would think that the Boeing wouldn't actually, I mean, okay, so let me just say that it's not out of the question because there's a guy, this guy named Max Legali who developed this, but you can do the whole thing where instead of so the way that, you know, the standard thing is that you take a silicon wafer and then you grow silicon germanium on top and then you make your quantum well, okay. But you can do it where you put it on oxide and then you end up with a thin membrane. And Mark Erickson has demonstrated that you can, you know, you can do everything. You can make quantum dots and all this on membranes, okay. And the reason why I'm a little dubious is because when you do the membrane, you know, they have, this costs almost no energy at all, okay. And so you're not changing the band structure. And this was relevant because, you know, the thing was, putting the membrane so it was flat. So what you do is you take it, it's oxide, you dissolve it in some sort of acid, I forget which one. You take it off and then you put it on another substrate and it sticks there. And then you end up where it doesn't lie quite flat and you get wrinkles on it and stuff.
Yeah, it doesn't take mechanical energy, but I think it does introduce strain.
Well, but the strain is really small because it's just in any, so I'd have to work it out, but I'm a little dubious because it's so floppy, right?
Yeah.
So the strain is large, but the stress is small.
Yeah.
You know what I mean? So I'd have to think about it to be sure that I was telling you the right thing. But that's my worry, is just that the energy, it's true, but the energy, the change in the band structure, I think is tiny. Because we were banking on it in the other direction, right? Where, oh, it's strained, but the stress is small, even though the strain is large. Oh. And again, it's because it's a bending mode and it's really thin, and so the energy cost goes like it's like the thickness cubed or something. I forget. But it's some reasonably high power of the thickness. So that's why I'm mumbling about that, because I think the band structure, it's hard to change the band structure that way.
I think it's actually the strain and not the stress that changes the band structure, but that's okay.
You think?
The spacing of the atoms.
Oh, I see what you're saying, but the thing is, okay, it's like if you do this,
I trust you.
Yeah, no, I mean, the thing is, again, it's just like you have a piece of, you know, I have a phone,
I trust
and it's
you.
like really doesn't want to move, right? And then I have like something like this, and again, it's not like the atoms are moving, you know, it really is like a geometrical effect, okay, that the energy cost is just really low.
Okay.
But you're saying, oh, but that's just because, let me think about it more. I mean, I may have been thinking about it backwards, but the thing is, we can do it. Yeah, it's something that could be done experimentally.
Okay.
So thanks for the suggestion, because now I have to think about it, because you know, Mark was working on these things, you know, really like thin membranes with these guys in them. I mean, that was something that, you know we can do. We may even have, but you know, okay. And I don't know that we've ever measured the band structure. But I know we thought about it. If you're interested, send me an email, and I'll write to the person and then tell you what. Yeah. But I know you know what I mean. It's like a good enough question that it has been looked into. But I don't. And I thought it was too small, but I could be wrong. Okay.
Hello?
Yeah.
Okay. I was waiting for Dan, but I think we're out of questions as usual.
Okay.
people are welcome to either email myself and Dan to pass along questions to you, or email you directly if they have questions, because we do end up having students who have questions sometimes afterwards.
Oh, no, no, that's fine.
Thank you very much for the wonderful talk. This is great.
No, thanks.
I worked a little bit on silicon-based qubits at Santa, so
okay,
we
great.
appreciate it.
Okay, thank you. All right. Okay. All right.
Do you have any meetings with people